Section 7.4 is on inverses of trigonometric functions. We're going to be finding values of inverse trigonometric functions, simplifying expressions involving inverse trigonometric functions, simplifying expressions involving composition of trigonometric functions analytically, and simplifying expressions involving inverse trigonometric functions by making a drawing and reading off the appropriate ratios. Right. So we have dealt with inverse trigonometric functions before in chapter 6. And so a quick review of inverses. If a function is like a machine that takes inputs and turns them into outputs. So if the function is like a machine that takes inputs and turns them into outputs, what does the function's inverse do? Well, the function's inverse is going to do the reverse. It's going to take the outputs from the original function and turn them back into inputs. For example, if we consider one of our trigonometric functions, let's go ahead and use cosine. Sine gets all the use. So let's take the cosine function, where the cosine of theta, some angle, is equal to the value x. Then the inverse function, which can be written as either arc cosine or as inverse cosine. Either of those is going to take in the input x and return the output theta. So opposite of what the function does. The input of the function theta has an output of x. For the reverse, the outputs of the original function return the inputs to the original function. And once again, we know for trigonometric functions that there are many ways to state their inverse. We can use the arc notation or the -1 inverse notation. There's no difference functionally between those two. It's just a difference in written notation. All right, so considering the graph of a function, if there are sections of the domain where the function is only increasing or decreasing, what does that mean about its inverse there? We had this definition a while ago. We said that if the function is only increasing on a particular region, then this graph is 1 to 1 on that region, and therefore the inverse exists. Okay, so if the function is only increasing or only decreasing, this is an example of one that is only increasing. That makes it 1 to 1, passes the horizontal line test. And so if you were able to flip that, it would make the inverse function exist and therefore be a function. So when I say the inverse exists, it means that the inverse is a function. Therefore, for any trigonometric function, we have to define its inverse function by restricting the domain of the original function or defining a region over which the original function is 1 to 1. So defining a region over which the original function is 1 to 1. So defining or restricting is my word for that as well. So for example, if we take a look at the graph of sine of x, We know, for example, on this graph, we've got our markers for 0, pi halves, pi, 3 pi halves, and 2 pi. 1 period is 2 pi, and our heights of 1 and -1. If I wanted to find, let me label a couple more back here. This would be negative pi halves and negative pi. If I wanted to find a region over which this function was strictly increasing, I could start at 0, and I could think it's strictly increasing up until it gets to pi halves, but then it does begin decreasing. But also, that increase starts back here at negative pi halves. So for the function sine of x, we need to define or restrict the domain to be from negative pi halves to pi halves, because that is one area where it is strictly increasing. Now, you could choose an area where it's strictly decreasing, and you could have said from pi halves to 3 pi halves. We will typically choose whatever region gets us closest to the origin, which is the reason for choosing this area instead of this area or this area. There are, of course, many intervals where we could break sine. We're going to choose the one closest to the origin. We know that the range of the sine function is from -1 to 1, and that means for the inverse function, which is either listed as arcsine or inverse sine, your choice of notation right here, its domain and range, since they're inverses, x and y swap, so domain and range swap, its domain is going to be -1 to 1 from the range, and its range is going to be from negative pi halves to pi halves. So just a nice look at one example right here of restricting the domain of a function. This one's using the sine of x function to an interval over which it is 1 to 1. 1 to 1 can visually be seen by all increasing or all decreasing. All right, so let's take a look at the next page. It's going to detail what's happening with some of our trig functions. And it says, again, what we were mentioning in the previous page, we can think of square root of x as part of the function x squared. It's restricted on the domain. The inverse is restricted on the domain x positive, because the other half, of course, would need to be the negative square root of x. So we consider specific restrictions on these functions because they repeat. Okay, so we mentioned that. And we're looking now at y equals inverse sine of x or arc sine of x, depending on which of those notations you prefer. And the domain, as we just saw on the previous page for the inverse function, is going to be -1 to 1, and the range is going to be negative pi halves to pi halves, and we've already seen on the previous page that example of y. So let's take a quick thought or look here at the cosine function. For the cosine function, the original cosine function, not the inverse here, but the original cosine function, looks like this. And if I wanted it to be just increasing or just decreasing closest to the origin, I would look at this portion of it. I also could consider the portion on the left side. They're equally close to the origin, but we typically choose things that have positive values when possible. And so the domain on the cosine function would be restricted between 0 and pi. We know, of course, the range is -1 to 1. And so when you flip those around for the cosine function here, when we're talking about the inverse cosine function or the arc cosine function, its domain is going to be opposite of the original. The original had a range of -1 to 1, so its domain is -1 to 1. And its range will be 0 to pi, because that is the first interval where cosine is only decreasing. So 0 to pi. Okay, just kind of showing the graph of cosine to help understand what's happening here with the graph of arc cosine. Before we look at tangent, let's just take a look down here. This is what the graph of the inverse sine of x function looks like. So we were thinking about that sine curve. Remember, we had drawn that portion of the sine curve as being here. And if you imagine taking this increasing portion of the sine curve and reflecting across y equals x, this is what it looks like. Okay, so the rest of it would up to here and down to here because you're flipping the x and y axes. So that's what the inverse sine function looks like graphed. And then similarly for cosine, the inverse cosine or arc cosine function is going to look like this. So imagine again reflecting this. This starts at the ordered pair 0, 1. So if you flip that, it's going to be at 1, 0. And then it ends down here at the ordered pair pi, negative 1. So you flip that, it's going to be negative 1 pi. And so we've got our reflection here across y equals x for the inverse cosine function. All right, continuing on, thinking about the tangent graph. So if you remember from earlier or use decimals, what the tangent graph looks like. We have these asymptotes, and then the curve repeats. But if you're going to be looking at an interval over which it is strictly increasing, any one of those is going to do it. And those asymptotes were at pi halves and negative pi halves. So for the tangent function, it's inverse function, arc tangent of x or inverse tangent of x. The range, these things in the original tangent function went up to infinity, down to negative infinity. So the domain of the inverse function is going to be negative infinity to positive infinity. And then we have to restrict this to start at negative pi halves and go to pi halves. Not included because those are the location of asymptotes. And so those are going to be the range of the inverse. So when we flip that over, this is what our inverse tangent or arctangent function is going to look like. All right. When interpreting the inverse trig functions, we can read them as the angle whose trig value is blank. So that means that the output is an angle and the input is the ratio, right? So input of the trig functions is the ratio of the inverse trig functions, and the output is the angle. So when we are asked what the inverse cosine of 0 is, 0 is the ratio. We want to know what the answer to the angle is. So for the cosine function, again, I'm thinking about unit circle right here. We remember on the unit circle, we're of the form cosine x comma sine x. So I need the x coordinate, the cosine function, to be equal to 0. So this is 1, 0. That's the cosine is 1. This is 0, 1. And this is 0, negative 1. In order for this to be a function, though, we did restrict cosine so that it's between 0 and pi. So the angles must be top half only on the unit circle, so that the angles are between 0 and pi. So we're able to output angles between 0 and pi. So the only angle between 0 and pi, whose inverse cosine is equal to 0, is going to be the angle up here at pi halves. So the answer is going to be the angle pi halves. I can use a calculator to get that value. It's going to give me the value in decimal form, and I could figure it out by dividing off pi if I needed to. But for special angles, we're better off thinking about them in terms of the unit circles. That's how I want to think about these. Okay. The next one, I need the arc sine to be equal to the negative square root of 3 over 2. So I'm going to think about my unit circle. And on the sine function, I remember that the outputs need to be between negative pi halves and pi halves. So for the sine function, I'm looking between the angle negative pi halves and pi halves for the outputs of arc sine. And I need it to be negative root 3 over 2. So that's going to be height taller. So it's going to be down here. It's got a reference angle up here with the height taller. Again, this is pi 6. That's pi thirds. When we go backwards, this angle would be negative pi thirds. So this angle is going to be negative pi thirds. In case you didn't notice, in the sine function, we have negative angles past 0 and the positive angles above. So our angles are going to be outputted as negative angles if they have their sine values being negative. All right. Once again, the cosine ratio is positive in quadrant 1, negative in quadrant 2. The sine value is positive in quadrant 1, negative in quadrant 4. Okay, and then this next one is the cosecant. Now, cosecant is a little harder for me to read off of a unit circle because the unit circle is about cosine and sine. But I can think about how I can relate cosecant there into the to the sine, right? Cosecant to the sine. So let's make a few notes right here. We know that if cosecant inverse of 2, whatever it is, it's going to be equal to some angle, such that 2 would be equal to the cosecant of that angle. So if we apply the function to both sides, cosecant of arc cosecant is going to be just 2, and I have cosecant of the angle. What I'm trying to do is use a reciprocal identity to write this in terms of sine. So this is going to be 1 over sine of theta, multiply the sine over. 2 sine of theta is going to be equal to 1, and if I divide off the 2, sine of theta is going to be 1/2. So what I'm looking for is the angle whose arc sine or inverse sine is equal to 1/2. So just a demonstration right here of the fact that because sine and cosecant are reciprocal functions, the cosecant of 2 is going to be equal, the arc cosecant of 2 is going to be equal to the arc sine or the sine inverse of 1/2. Okay. So where that would occur on my unit circle, we know for sine, we're going to be on the left side between negative pi halves and pi halves. And if I want the sine value to be half, that's going to happen at the angle pi sixths. That's a positive, so it's going to happen at the positive angle. So the answer is going to be pi sixths. All right, now I am going to take a look at these with a calculator. I think it's useful to see what it can and cannot do for us. So let me clear this. If I ask for the arc cosine, I need to type it with the ARC if I'm typing, of 0, I do get a decimal value that is equivalent to pi over 2. So if I had that value and I divided it by pi, I could see that it was the fraction 1/2 of pi. So that would be one way of manipulating the calculator in terms of helping me out here. Let's check the next one. I'm going to use the arc sine of the negative square root of 3 over 2. And again, it's some decimal. If I divide by pi, I can see it's the fraction negative 1/3, so negative pi thirds is the angle. And for this one here, I can enter the arc cosecant of 2. And once again, if I divide by pi, I get the fraction 1/6. So we're able to confirm that my answer is pi sixths. So by dividing these by pi, I'm actually able to use the calculator to get the values. But it's also really important and interesting to understand how you can figure them out just from knowing the unit circle as well. Now, let me keep my calculator handy as I get to the next page. On the next page, 158 and negative 6.19, like these things are not perfect angles. So I'm going to need to use the calculator in order to get answers in terms of the angles for these. So if I find the inverse tan or arc tan of the angle or of the ratio, this is the ratio here inputted, of the ratio 158, that gives me an answer of 1.564, and that is in radians. Remember, radians are unitless, so I don't need to write a unit for radians. If I did want to know in degrees, I could switch into degrees and say, or about 89.6 degrees. But unless you're told to use degrees, we are going to be focusing on radian measure here still. Sometimes it's useful in terms of figuring out how big something is, like knowing that this is just below 90 is something that's easier for me to determine in terms of degrees than it is in terms of radians. So being able to compare them quickly is nice. Let's go back into radians for the next one. Let's do the inverse sine, so the arc sine of negative 0.6199. Again, in radians, this gives us a radian angle of negative 0.6686 in radians. You don't have to write radians in parentheses. I'm just making an extra emphasis that this is not a degree measure, it's a radian measure. And it is a negative angle, so it's an angle that's down in quadrant 4. And I have typed these with the arc notation. It's just my preference. So instead of having to find the inverse sine button and clicking on that, I like to be able to type instead. I forgot the decimal place. That's why it's not working for me. There we go. Now, of course, you get the same thing. And so this last one's actually listed as arc cosine. So again, I'm going to type that one as arc cosine of negative 0.9. It's supposed to be a negative. Negative 0.9810. This comes out in radian measure as an angle of about 2.946. 3 in radians. Now, I am keeping 4 places or 3 or 4 places when I write these down in radians because radian measure is a lot smaller than degree measure. 89.6 is a larger number, so the 89 is going to take a lot more of that precedence. But we'll use more decimal places with the smaller radian values than we would need with degree measure in order to keep accuracy. So I have intentionally written more places if I'm using radians. All right, I could convert these to degrees, of course, if I wanted to. We'll do one more in degrees. This one is approximately 168.8 in degree measure. You can see the other one up above if you wanted to write that one in as well. All right, so next, as a recap of previous material, finish filling in the tables below. So this table is filled in for us. For sine, the full domain is negative infinity to infinity, and the range is negative 1 to 1. We know if we're going to find its inverse, though, that domain gets restricted. So we're going to fill in the arc sine information. So this is our sine function. We want to fill in the information for arc sine. So the arc sine function, its domain comes from the range. And so its domain is negative 1 to 1. And its range, remember the sine function had to get restricted. So the sine function would have looked like this. And if you're going to restrict that in such a way that it's only increasing or only decreasing, you're going to restrict that to be between negative pi halves and pi halves. So that's going to be the range of the arc sine function. We saw this just on the previous page. Similarly, for our cosine function and our arc cosine function, The range of cosines, -1 to 1. So the domain of arc cosine is -1 to 1. And our cosine function, we have to restrict between 0 and pi in order for it to be 1 to 1. So the range of arc cosine is going to be 0 to pi. For tangent, it's all real numbers except all multiples of pi halves. So it's got asymptotes at pi halves and negative pi halves. So for arctangent, the domain is going to be the range of tangent, which is -infinity to infinity. And then we're going to get that negative pi halves to pi halves, which is the distance between the two asymptotes that are closest to the origin. For cosecant, it's all numbers except k pi, so that would be all numbers except 0 times pi, 1 times pi, 2 times pi, etc. So if we flip this over to the domain to the range, the closest set to the origin would be from 0 to pi, and there are asymptotes. So instead of the brackets 0 to pi, it's going to be 0 to pi with parentheses, similar to what we had up here for the arc cosine function. However, you know what? Hold on. Yeah, okay. Yep. Sorry. I actually need to look at this again real quick. I was remembering that this is where the locations of the asymptotes, this is not the domain, it's all numbers except these. So hang on. I haven't drawn this one like I previously drew tangent, so let me make a quick fix here. So back when we drew tangent, we said that the tangent function looked like this, and we had those asymptotes at negative pi halves and pi halves. So we knew that that was going to be the range of the cosecant function, or the the range of the arctangent function. The cosecant function looks like we have asymptotes at 0 and pi, and if you remember, we have these U shapes elsewhere. Okay, so that's what our cosecant function looks like. So let's continue and think about where the arc cosecant function is going to be defined. If I want to look at a region where it is strictly increasing or strictly decreasing, we are going to have to cut it at this non-asymptotic value of negative pi halves to be decreasing. And then we're going to cut it here as well, where it stops its decrease to put it closest to the origin. So we've got ourselves negative pi halves and pi halves. And then we have to exclude 0 because 0 is an asymptote. So when we get to the range, our range is going to go from negative pi halves up to 0. And then it's going to go from 0 up to pi halves. That's going to be the restricted domain and the cosecant function. That's going to be the range of the arc cosecant function. We do get all of the outputs in that slice. So we are going to have as our domain the full -infinity to -1. And then we're going to continue on with the 1 to infinity. Okay, I'm going to make sure we draw the picture for arcsecant as we talk about this one. So for arcsecant, it's the similar U-type shapes, but the U's are right on the y-axis, not offset, because the asymptotes are at the negative pi halves, and so pi is going to be here at the other U. And this time, if I want all increasing, We're all decreasing. We're going to go here to here. And so that's going to be from 0 to pi halves. And then we get a break because pi halves is an asymptote. And then we'll go from pi halves to pi. Okay, now on the domain of the arc secant, it is equal to the range of secant. So it's the same thing as we're going to have there for the arc cosecant. It's going to be again from negative infinity to negative 1, and then 1 to infinity. Last, we've got our tangent, cotangent. We've seen what tangent looks like. And so the cotangent function, instead of having the asymptotes at the pi halves multiples, it has them at the k pi multiples. So it's going to have an asymptote right through the y-axis, and this next one here is going to be at pi. So the slice on tangent, or cotangent, that's all increasing, is going to be from 0 to pi. So we're going to have from 0 to pi being the outputs for arc cotangent, and then these go all the way up, all the way down. So arc cotangent is going to go from inputs negative infinity to infinity. Okay. So when we initially think about here the domain and range of the arc or inverse functions, it's useful just to think about them in terms of the original 6 functions, since we can and already have studied what those pictures look like. And that helps us predict what these are going to look like. In the next topic, we're going to do some composition of trigonometric functions and their inverses. Recall from previous experience that if you have a function f of x and its inverse function f inverse, for all x in the domain of the inverse, we know that if we compose the function with its inverse, we're going to get that input back out. So you're going to say f inverse of x gives me something, but f of that something is back to x. So we're thinking about this pattern where x goes to some y and then it goes back to x when we apply both the function and the inverse function. And the same thing is going to happen in the reverse. If you apply the function first and then the inverse, which is actually what I drew up here, you get back to x as well. Apply both of them, we go in that full circular pattern. Sorry about that word there. That is, the functions and their inverses undo each other within their respective domains as mentioned. So we can put this together for use in trigonometric and inverse trigonometric functions. So sine of inverse sine of x is going to give us back to x. Cosine of inverse cosine of x is going to give us back to x. Tan of inverse tan of x is going to give us back to x. Similarly, you can go in the reverse. Inverse sine of sine of x, back to x. Inverse cosine of x, back to x. And inverse tan of tan x, back to x. One of the things that we have to keep a special mind here is that this is for all x's in the domain of arc cosine and all x's in the range of arc cosine. And so we are going to see those domain restrictions coming into play in some of these examples down here, and I'll let you know which ones we need to pay special attention to. So in this first one, we need to take the cosine of the arc cosine of square root of 3 over 2. So drawing out where this would be. So when cosine is equal to the square root of 3 over 2, that is going to be here when that's the x value. And in general, that occurs at either one of these angles. The arc cosine of the square root of 3 over 2 has to happen only in the top, right? Because arc cosine is going to return an angle that is between 0 and pi. So it's going to return this specific angle. And then you need to take the cosine of that specific angle, and it will be the square root of 3 over 2. So this one works exactly as expected. When you do the cosine of the arc cosine, you're going to get exactly the input back, just like these properties up here. Okay, so me color code these as working great as anticipated right here. Now, in the next one, we're going in that same direction where I need to do the sine of the arc sine of 1.8. So a little diagram of what this might look like. 1.8, that is a height ratio. But remember, on the unit circle, 1 is as high as we can get. So 1.8 as a height, it's too big. So that's not a possible input for the arc sine function. So this is going to be undefined. My diagram helped me notice that that was going to be a problem, and emphasizes that this is going to be equal to x for all x in the domain of arc sine, and 1.8 is not in the domain of arc sine. Recall that arc sine is only able to input domain values that are between -1 and 1. 1.8 is too big. So because of this fact here, we are undefined. We're unable to answer that question. It's not equal to 1.8. So you have to use caution when trying to cancel out two functions. Make sure that the value that you're inputting is a possible input value for the domain of the innermost function. It's not in this case here. Okay, let's look at the bottom two. In this one, I need the arc sine of 3 pi over 4. So again, diagram, unit circle. On the unit circle, the angle 3 pi over 4 is here. And when I take the sine of that value, it's going to give me the y coordinate, whatever it happens to be, of that point. It is on the unit circle, so I know what it is, but that's not part of what I need right here. But then I need to take the arc sine of that same value. So I'm going to get a point that has the same y coordinate, but remember that arc sine is going to return angles that are between -pi12 and pi12. So the angle 3 pi4 is not the one that's going to come out. The one that's going to come out of arc sine is going to be the angle over here that has the same reference angle, and that is going to be the angle pi4. So it's going to be these have the same reference angle of pi4 away from the x-axis. So 1 pi minus 3 pi4 is 1 pi4. They match up. Okay, remembering that this is 1 pi, right? If you're going to figure out how big that angle is, pi minus 3 pi4 is 1/4. And from your unit circle, you'll know that these are opposite of each other. Therefore, I have the same sine value. So this comes back as pi4. So the answer to this is pi4. They're not going to cross off exactly, but they do return an angle whose reference angle is the same. And that is because this needs to be, they're only equal to x for all x that are in the range of arc sine. And this angle, 3 pi4, is not in the range of arc sine. This one is. Always make the diagrams when you're doing these so you can verify whether the angle comes back out or the side comes back out, depending on which order you're doing this. Okay. This one over here is actually not as much a use of one of these properties because it's not arc cosine of cosine or arc sine of sine. It's arc cosine of sine of pi halves, but I can still evaluate it with the same method here on the unit circle. We're going to consider where the angle pi halves is. We know that's up here on the y-axis. And I know that ordered pair would be 0, 1. And so if I evaluate this, the answer to the sine of pi halves, the sine of pi halves is going to give us the y value, which is 1. And then I'm going to need to do the arc cosine of 1. And remember that the arc cosine of 1 is going to be from this point right here, 1, 0, that has a cosine value of 1, and it's going to return the angle of 0. So the answer to this one is going to be the angle 0. The arc cosine function outputs an angle, and the angle 0 or 2 pi or whatever, using the simplest notation, of course, is 0, is going to match up with the inverse cosine of the sine of pi halves. Okay, I want to check a few of these just to see how they work out. Let's check the bottom two. So in the bottom two, if we do the arc sine, I'll use that notation, the arc sine of the sine of 3 pi over, I gotta use parentheses there, 3 pi over 4, it comes out as this angle. And if I divide that by pi, I can see that it did come out as pi fourths. So I'm just checking my answer here using the calculator. The rationale all comes from how the unit circle works. And let's just check this last one here as well. I'm going to type it with arc cosine just for ease of typing of the sine of pi halves. And again, it does come out as 0 from that rationale we used there on the unit circle. Okay, so we're going to continue to our last page here. In example 4, we get to use the sketch of a reference triangle to find these following ratios. So we've been doing that on the previous page, sketching them on the unit circle. Now we're going to sketch them on a reference triangle off of the unit circle again, so same kind of starting point. But these ones, big difference is they're not special ratios. So these are not things that I can identify as immediate angles on the unit circle based on their ratios. So I'm going to estimate their position. So for tangent, I need my tangent to be my ratio of the sine over cosine, and it's positive. I know that tangent is going to output, arctangent I should say, inverse tangent, is going to output things that are between negative pi halves and pi halves. So this would be in quadrants 4 or 1. Because this is a positive, it's got to be something somewhere in quadrant 1. So I'm imagining this triangle right here. And so for this triangle right here that we're imagining, just going to say like this is the triangle formed by this angle. I don't need to get a decimal version of this angle. Instead, I say that whatever this angle is, its tangent would be the square root of 3 over 4, meaning that its ratio of a side opposite over a side adjacent would be square root of 3 over 4. And I could use the Pythagorean theorem to find the missing side of this triangle. There are also a couple of different ways to set this up. So I'm going to work with this way for right now, but I just want to mention that since we do typically work in a unit circle, I also could set this up. Let me see. I was thinking about setting this up with a 1 right here, but I've got to figure out the way that ratio would come out. I would need to solve it first. So I'm going to go back to what I was thinking right here. So I'm going to solve this first, and then we'll work all that out right here. So let's think about Pythagorean theorem, which says square root of 3 squared plus 4 squared equals c squared. So that's 3 plus 16 equals c squared. And so that is 19 equals c squared. So square root of 19 is c. Okay, this is going to be the simplest way to set this triangle up. If I wanted to draw the triangle as on the unit circle, I would have to divide each of these by square root of 19. I just didn't know what number I would need to divide them by until I solved for it. So this is also square root of 3 over square root of 19 over 4 over square root of 19. But in the tangent ratio, the square root of 19 has already been simplified out when you divide those two things. So I didn't have a way of getting it immediately in the unit circle. So it's okay to use, remember that this tangent is going to be the same on any circle, not just the unit circle, because the angle is the same. So I'm drawing a triangle that is not on the unit circle, and I'm trying to tell you that that is okay because these would reduce out when you divided the tangent ratio. So we're going to stick with this triangle. Okay, so didn't mean to overcomplicate that, just trying to make sure we explain why it's okay to not use a unit circle or a radius of 1 right here. A radius of 1 doesn't work with those two values. We need that square root of 19 in there somewhere. Now, long story short, what I want is not the angle itself, but what I want is the cosine of this angle, right? So the cosine of this angle is going to be the measure of its adjacent side over its hypotenuse side. So it's going to be 4 over the square root of 19. I can do this on the calculator, but on the calculator, I can't get the exact value. So if I do this on the calculator, the cosine of the arctan of the square root of 3 over 4 comes out as the decimal equivalent to the fraction 4 over the square root of 19. The decimal numbers match up, but by using a reference triangle, I was able to solve for this value exactly. And again, I solved for that exactly by using the fact that the cosine was a ratio of the side adjacent over the side hypotenuse. Okay, let's give this another try in the next one. Now we're going to be finding the tangent of the arctangent of point 1. So we're going to draw ourselves a circle. And on this circle, the sine value is 0.1. So sine is a height ratio. It's going to be 0.1. And that's going to be out here because we know that the sine function, instead of being out here, for example, the arcsine function is going to have output angles that are in either quadrants 1 or 2. So it has to be this one. So we've got this triangle, just made it a little bigger. And sine is a ratio of opposite over a hypotenuse. So I've just written 0.1 as 0.1 over 1. And now I need to find the missing side. So I'll use a squared plus 0.1 squared equals 1 squared. A squared plus, when you square 0.1, you get 0.01. Square 1, you get 1. So a squared is 0.9 9 when you subtract that over. And if you take the square root of both sides, it's that number. That's not going to be an exact number. We could write it in fraction form if we wanted it exact, which apparently we do. So 0.99 in fraction form is 99 over 100. So A is going to be equal to the square root of 99 over the square root of 100. I know the square root of 100 is 10, and 99 is 9 times 11. So the square root of 9 is 3, and I can't evaluate the square root of 11. So the A value, this square root of 0.99, has got to be equal to 3 times the square root of 11 over 10. You can see that those values match up, but now I'm going to be able to express this exactly. So this value here is 3 times the square root of 11 over 10. And I want the tangent. Let's go ahead and write this 0.1 as 1/10. That's just the fraction equivalent of the decimal 0.1. And when we do the tangent, we know that tangent is going to take the opposite divided by the adjacent to do that tangent. So the answer we're looking for is going to take the 1/10 divided by this 3 square root of 11 over 10, or 1/10 times the reciprocal, 10 over 3 square root of 11. The 10s reduce out, and we have 1 over 3 square root of 11. Okay, so this is equal to 1 over 3 square root of 11. Okay, absolutely fun to check these, so let's do that. The tangent of the arc sine of 0.1 matches with 1 over 3 times the square root of 11. And yes, those are decimal equivalents. But now we've been able to find the exact form of that answer. Okay, we're going to continue that in the next two. Although in the next two, notice that we're going to have a variable as one of the sides in the triangle. That's okay. So let's start with tangent equal to a over 3. So tangent, once again, uses negative pi halves to pi halves. And we're going to assume that the value of a is a positive. It's not something I know, but typically we assume our variables are working with are positive, which is going to put us up here somewhere in quadrant 1. And if we drop that down, we can draw in what our triangle looks like here. Tangent uses ratio opposite for a over adjacent for 3, and we're going to need to solve for the hypotenuse. So a squared plus 3 squared equals c squared. So a squared plus 9 is c squared. And I am looking for the hypotenuse, so I just want to take the square root of both sides. So square root of a squared plus 9 is c. We are technically doing positive and negative, but hypotenuses are always positive. So this is going to be the square root of a squared plus 9. And now I need the sine of that triangle. We know that the sine, that's what we're trying to do next, is the opposite over the hypotenuse. So opposite over hypotenuse is going to be a over the square root of a squared plus 9. And the last one, the cotangent of the arc sine of P over Q. So once again, thinking about a circle whose ratio is P over Q. The arc functions on these ones, tan, sine, cotan, they've all actually been ones, sine and cosine ones, or sine and tan ones. There's been no cosine. So I've been working on the right-hand side instead of the top for I would have for cosine. But regardless, if that had been a sine or a cosine, we are assuming both positive. So we're always going to be in quadrant 1 for those variable ones. So I'm going to have myself some triangle in quadrant 1 here that I'm looking at. Sine is going to be P over Q opposite hypotenuse. And we're going to find this missing side. So let's call that A. So A squared plus P squared equals Q squared. A squared would be equal to Q squared minus P squared if we subtract that over. And then we'll take the square root of both sides and we'll get positive and negative square root of Q squared minus P squared. We are going to, again, use the positive because we are in quadrant 1. We're assuming that P and Q are positive and that we're not in quadrant 4 down here with a negative for our A value. So we're going to actually doesn't matter. It's going to have to be positive. And I was just thinking about what A is. Since A is this distance, A has to be positive because it's only negative. X coordinate over here on the other side. I don't have that. So I've got myself Q squared minus P squared right there. Then I need the cotangent. And the cotangent is going to be the adjacent divided by the opposite. It's the opposite of what tangent is, the reciprocal of tangent. So that is the square root of Q squared minus P squared divided by P. So in all of these, we've used the inner arc trig function to set up our triangle. We've solved the triangle and then taken the outer trig function of the triangle to get the ratio. All right, there is one last example at the bottom of this page. In this example, we've got an airplane that is flying at an altitude of 2,000 meters towards an island. The straight line distance from the airplane to the island is m meters along a specific angle. Express the angle of depression as a function of m. Okay. So I've got an airplane and I've got an island. And the airplane is flying, this is my water, at an altitude of 2,000 meters. So the altitude is going to be its height, and that height is going to be 2,000 meters. And then the straight line distance from the plane to the island is m meters along a specific angle. Express the angle of depression as a function of m. So remember that the angle of depression, which would be this angle, is equal to the angle of elevation, which would be this angle. And we're going to be using the angle of elevation because it's inside of our triangle. So the triangle is formed from these three sides. Okay. In terms of this angle, I know opposite and hypotenuse. So I could say that I know the sine of the angle is equal to 2,000 divided by m. Or I could have, had I wanted m to be on the top, have used the cosecant instead. You can use the sine function for 2,000 over m or the cosecant function for m over 2,000. Doesn't matter. I want to express the angle as a function of m, which means I need to solve for that angle. That's the thing I want to have. The angle needs to be my output. So the angle is going to be equal to the inverse sine or the arc sine of 2000 over m. So as a function, theta of m is equal to the arc sine of 2000 over m. So I've expressed the angle as a function of, in this case, it's the arc sine function of 2000 divided by m. If you chose instead to set this up with the cosecant function, your answer would have looked a little different. You just would have ended up with the arc cosecant of m over 2000 instead. So there's not one unique answer. That would be an alternative answer if you had used that ratio instead. But you definitely needed to use one of those with the information you were given, since you had sides opposite and side hypotenuse.